here in person. And our guest today is Alberto Vela Martín. And for those who don't know him yet, he's from Bremen, University Bremen, obviously, working in the group of Mark Avila. And that is the manager or director of this tower, which you might have seen in the University of Bremen. And that's a tower where you can drop things and then they fall down without gravity, and you can study zero gravity for a short time, which is of course interesting for all kinds of things because gravity is the most important force which we have everywhere. Maybe in the sun or somewhere, but here on Earth it's most important. So, and Alberto will tell us something about new perspectives in the turbulent energy cascade with or without gravity.
Yeah, gravity is important for the cascade. I think probably.
Can you just press got it?
But for the cascade, incompressible at least not, but maybe compressible it is. So thanks for having me here today. I'd like to thank Jens Rademacher for inviting me to this talk, and I'll be talking about quite a fundamental topic, at least in my opinion. I know that I am not from the earth sciences community, but I think you might find this content interesting for at least anything that is related to fluids. And I know that this group is well investigates energy transfer in the atmosphere, and I'll be talking exactly about that energy transfer, only that in a very simplified and ideal setup. And the title of the talk is a little bit passing, like non-equilibrium fluxes, but I'll show what that means shortly. So I'll be talking about turbulence. Probably you know what turbulence is. You've sometimes had a direct experience with turbulence, like for example with the smoke of a cigar. But turbulence is not only at the scale of human life, but it's everywhere. You can find it in planes, in wind farms, and also, of course, as you know already, in the atmosphere. And it's important everywhere. I study turbulence because I'm an aerospace engineer, so I'm mostly, or in my education, I was mostly interested in turbulence as a way of knowing how friction affects vehicles in the atmosphere, or for example, how you can move a liquid through a pipe, and try to find out whether we can somehow prevent turbulence from dissipating energy and wasting resources. However, I did my thesis in Madrid on a very fundamental topic of entropy. This idea of irreversibility, the arrow of time, is quite a classical concept, but it's in my opinion quite important. And that's what I will be talking about today, in relation in particular to fluid mechanics. And well, I finished my PhD I think more recently 2 years ago, a little bit more. And now I'm, as I said before, I'm right now at Uni Bremen with Professor Mark Avila. First, I will also talk about other projects I'm doing with Mark Avila. Today, I will talk mostly about the things that are related to my thesis and some other work that I did afterwards. But I'm doing other stuff now in Bremen that you eventually might be interested in. The first one is well, try to find out how drops break in turbulence. It's an important problem for the industry. They simply put a drop in turbulence and you let it evolve with time and see how long it takes for it to break, how it breaks. And it's related to, well, emulsions in general. We're trying to figure out the typical statistics of breakup. We find that this process is memoryless, and then we can find the typical breakup rate, and we're trying to devise models that can actually go into something applied or industrial. But still, this work is also quite fundamental. And we also have another project on which you might be even more interested than the previous one, which is predictability. In this case of extreme events, this is right now a hot topic because of course, of climate change. And we're actually using, we're not calculating the Lyapunov exponents, we're not doing approximate measures of predictability, but actually running a huge number of simulations, up to 32 million of this 2D flow, and try to determine whether extreme events are predictable or not. And we have found some interesting results. We can find extreme events of dissipation in this Kolmogorov flow, which have actually the same magnitude and look very much the same, but one of them is very predictable, the other is not. And well, this work is ongoing, and we hope to have it published in some time. And now let's go to the motivation of this talk, the outline. I'll be talking about turbulent energy cascade, which is probably, it's a universal process that happens in all turbulent flows if the Reynolds number is large enough. Of course, in large scales, the behavior of the flow might depend on whether you're looking at a wind farm or an engine or even a hurricane. But if you make sure that the Reynolds number is large enough and you go deep down into the detail, in the end, you will find always the same process, which is a cascade. Okay, there's a transfer of energy from the large to the small scales, and this is somehow something that allows energy to be dissipated. And I will talking about the energy cascade from a perspective that has been known for a long time, but has not been very extensively studied, which is the idea of a statistical mechanics of non-equilibrium, something that distinguishes systems in thermodynamic equilibrium with systems that are not, systems that are driven by a force or by something that is moving the thing. And I will show that studying this is a very fundamental problem, but has deep implications for modeling, and in particular for a technique that is called large-scale simulations, that some of you might be familiar with, because it's used mainly when, well, turbulence is very expensive to simulate, and most of the time you want to have a coarse grid, like probably what you do in the atmosphere. You have a grid distance of 1 kilometer, for example. You have to put a subgrid model. You have to put something there to make sure that the energy of the flow is actually well resolved. And finally, if I have time, so now we'll talk about another important topic that is also related to non-equilibrium, which is the idea of coherence. The fact that when you look at thermodynamic things in thermodynamic equilibrium, for example, a gas that is homogeneously distributed in a room, you don't see any structure, you don't see anything special. But when you drive that system out of equilibrium, for example, by putting some temperature gradient, you will see structures forming. You will see something coming up, some patterns that are repeated permanently. And this, I will try to convince you that is somehow related to non-equilibrium, and that you can actually learn how these patterns are formed by studying this idea of non-equilibrium or statistical mechanics. So why the cascade, or why is the main motivation to come up with this idea of the cascade? I'm an engineer, so I'll try to put this from a very practical perspective, why people came up with the idea of a cascade. And well, the problem is very simple. You just have a pipe and you're trying to move fluid through the pipe. You put a pressure gradient, so you put one pressure on one side and you put the pressure on the other, and you start trying to push the flow, because you're interested in moving things from one point to another. This is the same problem as an airplane, exactly the same thing, only an airplane is an open flow, but the idea works the same. And well, the idea is that you don't want to waste a lot of energy moving the flow, because you just want to move it and you don't want to spend energy. And that is, energy is money, and that's something that people are concerned about, which is normal, of course. And so you know that the dissipation has to do with kinematic viscosity, with the gradients, and you want to try to control this flow. So the first thing that you try to do as an engineer is try to reduce the kinematic viscosity, because it makes sense. I mean, it's something completely normal. You can, maybe if this is a liquid, you can change the temperature to make sure that the kinematic viscosity goes down, and you try to see what happens. Here we have the friction coefficient, which is something equivalent to dissipation. At the beginning, it starts going down. So you, as an engineer, say, "Oh, I have succeeded. This thing is working, nice." But all of a sudden, you see that it stagnates. Okay, and you can keep on trying to decrease the kinematic viscosity ad infinitum, but the thing doesn't work anymore. Okay, and this is probably one of the most amazing things about turbulence. Is something that is quite puzzling.
Goes up at the end.
Yeah, that is experimental uncertainty. I can assure you that it is. I mean, there is no physical evidence that the thing will change. It's actually from an experiment, but yeah. And the question, so the thing now you realize that the dissipation doesn't depend on the kinematic viscosity. It stays more or less constant, with some fluctuations, of course. And now you realize that the only way that this can remain constant with nu goes to zero is because the velocity gradients actually go to infinity, actually at the same rate as the kinematic viscosity. Okay, and you find out that in the end it doesn't really matter. The material properties of the flow doesn't really matter. What matters is the velocity by which you pump the liquid and the radius. And well, this is an empirical evidence, something that you can actually measure, and you need to find an explanation for this. And the explanation is the cascade. Okay, the idea that if the dissipation remains constant when the kinematic viscosity goes to zero, the only way this can happen is by the gradients to become arbitrarily large, to make sure that dissipation happens at the rate that is necessary. Okay, And the cascade assumes that turbulence is a multi-scale problem. So this is formed of many different scales. First, you have the integral scale, which is where the energy is injected. This depends on the flow you are considering. It might be a wind farm, might be an airplane, can be like a tornado, okay, whatever. It's something that is very large, okay? And it's anisotropic, and well, the flow at the large scales, they depend on actually the flow that you're looking at, okay? But then comes this process of the cascade, which is, okay, turbulence. You assume that turbulence as a way of generating smaller and smaller scales in a process that is stepwise, happens in the smaller steps or gaps, one by one. Okay, it's something that is called the inertial scales that have some properties. First one is that they are conservative. They don't depend on any of the properties of integral scales or dissipation scales. And an important ingredient here is that this energy transfer has to be local. I mean, there is nothing going from the very large scales to the smaller scales. So that in the end, there is a process by which the flow forgets all the details of where it came from, okay, of the large scales, and ends up in a sufficiently small, the energy ends up in a sufficiently small scale, so dissipation is possible, okay? So what happens here, if you relate it with the pipe flow experiment that I showed before, if you decrease the kinematic viscosity, this will just go down a little bit more, so that energy can be properly dissipated. And but in the small scale, you have something that looks a little bit like, well, these are vortices, like a soup of, like a soup of vortices, but which you assume that, because of this locality of the energy transfer, you assume that whatever happens there is sort of universal. And my interest here is now in understanding how this process takes place, how it happens, and what are the properties of this process of a cascade. And this is important because, as you understand now, the reason why turbulence is able to dissipate is because of the cascade. Okay, that's mainly the reason. And well, right now I just showed you that, like the distribution of energy in scales, and as I told you that there is this process of energy transfer from large to small scales, but we don't know much about the particular process that is involved in transferring that energy. Originally, in the time of the theory of the cascade goes back to Richardson in the 20s and was mostly developed statistically by Kolmogorov. And they somehow provided a cartoon picture of how this process of energy transfer happens, and it's related to the breakup of eddies. Things are very large, and they start breaking up into smaller and smaller pieces until they get to something small, and they actually dissipate. Okay, and this was quite a cartoonish picture. Let's say it's not very close to reality, but you can go actually to a direct numerical simulation. You can apply a filtering operation, which is try to isolate the flow at different scales, and you can try to visualize how these things look, and you actually get something that might resemble the picture of Richardson and Kolmogorov. Still, this doesn't mean that the energy cascade is a process that is fully understood. In fact, something that is still being investigated, and some people say that it's solved. I don't think it is. It's quite a complex problem, and well, this is what I want to talk about today, and I want to talk about why the energy cascade happens. I want to find out what is the actual reason, what is driving this process. As an engineer, I might be interested in dissipation, so I focus on that first. I say, okay, turbulence dissipate energy. This is something I can measure, that I can see in daily life, and then I just go there and measure the energy. I see that the energy is in the large scale, see that the gradients in the small scales, and I assume that the energy has to happen going from one place to another. And then I can make like a causal chain and go from here to there, and I say, okay, if the energy is in the large scales and dissipation is in the small scales and turbulence dissipate, then the cascade has to go from the large scale to the small scales. And this seems to be like a cause-effect reason, okay, that the fact that the cascade goes one way is because of the dissipation. And you might think already, because you are into atmospheric sciences, that in 2D the turbulence cascade goes actually the other way around. Okay, and that's something I will explain try to explain today from the perspective of statistical mechanics. And I will show that actually dissipation is not the cause of the cascade; it's something else. Okay, and it's something that we actually know very well, that we are very, very aware of it. And to show you this, I will propose an experiment. A very simple one, which is I take the Navier-Stokes equation in a very simple flow. This is 3D box of turbulence. So there are no large scales, there is no forcing, there is simply just turbulence in a periodic box. Okay, and I'm going to just let it decay, but instead of having the typical viscous term, I will have a model for the dissipation. This model will be something that will actually be removing energy, but with a very particular property. And the particular property I'm interested in is time reversibility. Okay, I will devise a model that looks very much like the dissipation, but that has a coefficient here that depends on u in a way that if I change u for minus u, it's equivalent to changing t for minus t. Okay, so with this system that looks very much like turbulence, okay, actually in the inertial range is actually the same. I can generate a simulation that goes forward in time, then I can just something very simple, change the sign of the velocity, and then I can come back. Okay, and what I have is initially this is the energy divided by initial energy. So start at 1, okay, and then I run forward in time, and of course, as I told you before, we expect the cascade to go down from the large to the small scales. Then the model is dissipating the energy and getting rid of it. Okay, and up to a point, I stop the simulation and I do something simple, just change the sign of the velocities. Okay, and now what happens? What I expected. The system is time reversible, so now I can get exactly the same thing going backwards in time. Okay, and you might think, okay, this is quite normal, what you would expect, because you have set up the system to be reversible, so it's understandable. And this is okay. It's what you would like. Okay, but then let me propose this experiment. What is actually why am I so sure that whenever I start here with whatever initial condition, a random one, something, I will get a cascade that is going from the large scale to the small scales? I could have just by chance set up my system with this initial condition, and then I put it there, I run the simulations, and all of a sudden I have a cascade that goes from the small to large scales. There's actually nothing preventing the system from doing that, literally. Okay, so of course, you would have guessed already that in the first evolution, I said already, you have a cascade going down and then going up. And this tells you that both the inverse and the direct cascade are possible. They are accepted by the dynamics, only that one seems to be way more likely than the other. Okay, and now remember that the model is not doing anything here. The model is at the small scales. This is a model for the inertial range, and the viscosity in the end is something that is not important. It is important to get rid of the energy, but it doesn't matter how you get rid of it. Okay, as soon as there is something removing the energy, the cascade doesn't matter because of this idea.
This dissipation operator, if it's positive, definitely, if it's removing energy or something.
What?
Is it this dissipation parameter operator which you have? Is it positive, definite?
No, it can be negative, of course. Yeah. In the inverse cascade, is injecting the energy.
You put in energy at the end.
Yeah. You're putting energy in the small scales, and the cascade knows the way to take that energy and move it to the large scale. Okay, but this model is only acting in the small scales of the flow. And remember that there is a stepwise process in the energy cascade in which things forget where they come from or where they're going. So it is not the model is not relevant for this. You know, it's just a way to make the system reversible. You can actually do this experiment at high Reynolds number, and it will actually work the same. Even though you have dissipation in the small scale, you change the sign, and you will see part of the flow in the inertial range going up. Okay.
Here we don't see this inverse energy cascade, right? We just see the energy going up. Because
it's the next slide. Yeah. So now you go to the flow and you calculate the energy fluxes in a scale. Okay, this is how much energy is going from the large to the smaller scales, and as a function of a scale. And you see that when this is exactly when I reverse the time. Okay, the energy is negative, which means it is flowing backwards. Okay, and well, the important thing of this experiment is that. Well, you can actually see an inverse cascade, but the moment you perturb it, okay, you introduce a very small perturbation in the flow, the inverse cascade is destroyed. It doesn't survive. It's something that is not natural to the system. So let's say that you have I go to let's see, I start here, okay, I go all the way down, I take this initial condition, and instead of running exactly that initial condition, I put there a small perturbation, okay. So the energy should actually increase to the place where you expect it to go because of time reversibility. But what happens is that only a small perturbation will actually make the cascade to go forward again. You know, there will be a point in which the perturbations will grow large enough to destroy the inverse cascade. So the inverse cascade is possible because we know the system allows for an inverse cascade, but it's highly unlikely. First, because it is very difficult to find an initial condition that would actually lead to an inverse cascade. And second, because it is unstable, okay? It is destroyed when you perturb it. And this brings me to a way to explain why this happening is related to a very intuitive, the very intuitive idea of entropy, of the fact that there is that the cascade is not something that is directly imposed by the equation of motions, but that is probabilistic. You simply put your Navier-Stokes there with an initial condition. Your Navier-Stokes might generate an inverse cascade, only they don't do it because that is highly unlikely. But it is actually possible if you consider the equations of motion. And the most typical or most intuitive way of explaining this is a gas that is expanding in the vacuum. Okay, you take all the air of this room and you put it in one corner. Then you go out, you wait for some time, and then come back. And you know for sure that at the time you come back, the energy is going to be homogeneously distributed in the room. And that is something that is not imposed by the dynamics that are moving these particles. I mean, the dynamics that are moving these particles also allow for the gas to be all concentrated in one corner. Only that is highly likely. Okay, and there is the idea of entropy, and of course you say, okay, the gas is conservative, there is no dissipation, whereas in turbulence there is, but there is a sort of approximate system that reproduces part of the physics of the cascade, which is the truncated Euler equation, which is simply I take Navier-Stokes, I remove the viscosity, okay, and then I project everything into a finite set of Fourier modes, okay. This is mainly something that you do not to allow the equations to blow up, okay? And then you can define, you can actually define an entropy in phase space, you can partition phase space. And the same idea we have with the gas, we can have it with the Fourier coefficients, okay? I start with an initial condition in a particular region of phase space. This is equivalent to having energy in the large scales, okay? And then I just let it evolve. And the system can do whatever it wants, okay? It can actually explore all possible states that are accessible by the dynamics. Okay, I am not putting any restriction here. The restriction is that the dynamics conserve the energy, and it has to be conserved. Okay, there is no way you can do it. And then you start with this initial condition, you move a little bit, and the system starts spreading in phase space. Okay, this is like the general idea of chaos. And there is an important fact in the same way that there is a lot of space available here for the gas to expand. There is no reason for the gas to stay here. When this original state starts distributing in phase space, there is more available space in the smaller scales than there is available space in the larger scales. Okay, and automatically this spreading in phase space will generate an energy transfer. Okay, in the end, what you get is something that is in equilibrium, exactly like the gas, something that is covering the full phase space and gives you an energy spectrum which is equal to k squared. Which means that in the end, the energy is homogeneously distributed among all Fourier modes. There is nothing special in the Fourier mode, so everything distributes homogeneously. And this is something that necessarily implies that if you start with an initial condition where energy is in the larger scales, you will have to go with a high degree of probability to something that has energy distributed homogeneously. And this implies a direct energy cascade.
Explain why it's k squared.
Yeah, it's k squared because because it's a 3D flow. I mean, and if you it's a formula of the spectrum. I mean, it can be.
It could also be just flat, right? Equally distributed.
No, because okay, in a volume you have a volume and the spectrum is computed like with speed. No, how you call them? Yeah, the spectrum is calculated by doing the integral of the surface over the Fourier space, and that gives you a k squared spectrum. And maybe. Yeah.
It's two-dimensional.
Huh? No, it's three-dimensional. It's three-dimensional. Yeah.
Energy density that's related to that.
Yeah, you have a Fourier space is three-dimensional, and the spectrum is something that is calculated over something that has an area that goes like k squared. That's why that's why you get a k squared. Okay. But that's the definition of the 3D energy spectra. If you do 1D, it's a different thing. Okay. Yeah.
Distributed. Is it the entropy? Is it flat? Or what is?
What
is conserved or what is flat? What is constant?
Constant is the energy per mode. Yeah, only that. But the way the energy spectrum is constructed, you get a k squared. But the energy per mode is constant. there is, I mean, from a thermodynamic point of view, any of the modes, they are all the same. It's the same thing as here. You put all the particles, okay, and you cannot distinguish one particle from the other. They all have the same mass, you assume. And then on average, they will have the same energy, the same velocity distribution. It's exactly the same idea, only instead of particles, you have Fourier modes. And well, the problem is that this doesn't tell us much about the physics of the cascade, because it's something that works either for particles or it works for Fourier modes. It works for actually many systems that could actually be explained using the same argument, okay, or the drift of the system in time could be explained using the same argument. And I want to try to translate this increase of entropy, or how this arrow of time, into something that is related to actually the physics of turbulence. Okay, and you can probably go to a turbulent flow, start measuring a lot of stuff, and try to explain it in many different perspectives. I've chosen one that I think is relevant, which is looking at the velocity gradients, okay, at the structure of the flow, the topology, how the flow looks at every point in the, when you look at it, how it looks at every point in the domain, okay, in a domain. And for that, I choose something that's called the invariance of velocity gradient tensor. So in 3D turbulence, this is a 3x3 matrix, okay? And you can get 3 invariants, okay, of this matrix, invariants which are invariant with respect to rotations and translation of the frame of reference. And you get 2 invariants. One is R, which is related to the amplification of the rate of strain tensor and the amplification of the vorticity. And the other is Q, which is related to entropy and strain. Entropy is a measure of how fast the fluid is locally rotating, and the strain is a measure of how fast it's being deformed. Okay, so there are 2 fundamentally different things. There is a third invariant, which is 0 because of compressibility, so I'll not take care about that one. And if you take this R and Q invariants and you go to the flow and you measure them at every point, you make a 2D PDF, a probability distribution of these invariants. You get this shape, like a teardrop shape. And also an important thing is that these invariants can be, as I said before, related to the local topology of the flow. So when you have a dominant Q, okay, means that you have a dominant vorticity, the flow is rotating faster and is being compressed, stretched, and you have what you would call a vortex, okay. And the fact that it is in this part of the QR diagram means that whenever you have intense vorticity, it's usually being stretched. Okay, you have this mechanism of vortex stretching. And there is another feature that is relevant in this QR plot, is this tail here, where the strain is dominant, and means that you have a local topology where things are being compressed in one direction and stretched in 2 other directions. Okay, and well, you can make sort of a relationship between this 2D PDF with the local topology of the flow. As I said before, this is related to the vortices, these red things that you see here. And this part is related to the rate of strain tensor, which is what happens in the surrounding of vortices. Okay, so this gives you a pretty good description of the dynamics in terms of rotation and deformation, and also how deformation and rotation change with time, and also this related to the topology of the flow. And now I want to see how this QR plot changes when I do this experiment of changing the velocities or moving backwards in time, let's say, okay, to find out what is the feature of the flow that changes the most when I do that. So what is the feature of the flow that is more time asymmetric, okay? And I plot here the QR drop in the direct cascade. This is the one I showed before, and then I plot the QR drop in the inverse cascade, and you see that it's simply just taking one and moving it the other way around and putting it there. This is what you would expect because of time symmetry, okay? Then I can define an asymmetry function, which is the logarithm of how different are the probabilities of finding one of the topologies in the direct cascade with respect to the same topology in the inverse cascade. And if I look at the vorticity, so the part that is in the upper part of the diagram, what happens when vorticity is dominant is that, of course, you see some differences, but these differences are not so noticeable, okay? At least are not so noticeable compared to what happens in the lower part of the diagram, okay, where the strain is dominant. You see that there is a huge change between what happens in the time forward evolution and in the time backwards evolution. Okay? So, well, and this, I think intuitively it makes sense because let's say that you have a vortex, okay, that is rotating, it's doing something, and then you just change the sign of the velocities. The only thing that you're doing is changing the way the vortex rotates, okay? Now it is rotating the other way around, okay? And this, I understand for atmospheric sciences is important. I get it, but for turbulence, it's something that doesn't really matter. It's still a vortex, okay? It's doing the same, simply rotating. But whereas when you look at the rate of strain tensor and you change the sign, what happens is the fundamental topology of the way the flow is being deformed changes. Okay, in the direct cascade, you have something that is being mostly compressed in one direction and being stretched in the other two. Okay, and you find predominantly this type of geometry. Whereas when you go to the inverse cascade, you have exactly the opposite. Okay, you have two things that are compressing the flow, and two that are and one that is expanding it. Okay,
direction doesn't play a role.
Direction,
its space doesn't play a role in turbulence, right? In your isotropic turbulence.
The what?
The direction, any direction doesn't play.
No, it's isotropic. It's isotropic. Yeah. It's statistical isotropic, but locally you can define some axis.
And it doesn't matter if you stretch or compress in the one direction. If it's still the same thing, then it doesn't matter also.
If you take the rate of strain tensor and you average it over the full box, you get something that is isotropic, and it's true it doesn't have a direction. It's actually zero, but locally it matters. It matters to the equation. It matters to the way vorticity is generated and to the way vorticity is dissipated, or the way the strain is generated. So that something is statistically isotropic. Okay, the turbulence, sorry, isotropic turbulence is statistically isotropic, but that doesn't mean that locally the flow is isotropic. Actually, the flow is highly anisotropic.
It changes the dynamics in this way, that the stretching and compression.
Yeah,
it's changing sign, but then this will average out, right? Because it's isotropic, I would guess. But anyway,
no, so, yeah. I mean, it's a good point. It's isotropic, but when people say that something's isotropic in turbulence, they mean that it's statistically isotropic. You can go to the flow. If you're inside a vortex, I showed the vortex, there are something that very stretch. You get inside a vortex as an observer of the size of the vortex, you will be able to tell where the vortex is oriented that way or the vortex is oriented that other way. And then you take all the vortices in the flow, you start averaging them, and you get something that is isotropic. It's true. It will not matter. But locally, as an observer, you put yourself in a vortex, and you know the way the vortex is rotating. So that is relevant. It's relevant for the dynamics in general. Although statistically, it's something that whenever you average it, it's the same thing. Homogeneity and isotropy is are only concepts that make sense when you talk about statistics. Otherwise, I don't think. Yeah. So what you get from this picture is that okay, vorticity doesn't seem to be that relevant. Okay, for the direction of the system in time, whether it's the cascade is going down or it is going up. It seems to be more related to the rate of strain tensor. And well, you might complain that the velocity gradients, they are small scales by definition. They might not be speaking about the energy cascade. Okay. But you actually get this picture by filtering the flow, by only isolating scales within the inertial range. You get exactly the same picture. Okay, something that applies to the small scales and also to the inertial range. And so the conclusion seems that if you want to understand why the system goes one direction and doesn't go the other, vorticity might not be a very good indicator of that. You have to look to the rate of strain tensor, and then you can go to the Navier-Stokes equation. You can calculate the evolution equation for the rate of strain tensor. Try to find out why the flow is actually, why the rate of strain tensor is actually generating this type of topology, but not this type of topology. Okay, and you get an equation that, roughly speaking, goes something like, okay, the material derivative of the strain is something that is related to the self-amplification plus a pressure. Okay, self-amplification is simply the rate of strain tensor interacting with itself. Okay, and the pressure is something that is related to how the surrounding fluid is acting on the rate of strain, or the rate of strain tensor. Okay. And the difference between the two is that this self-amplification is local, okay, and it's deterministic. So whenever you put the rate of strain tensor with any particular configuration that you like, and you look at this term and you evolve this in time, you always know where it is going to end. There is nothing that can generate any uncertainty in that evolution. It's something that is completely local, depends only on how you start. Okay, this is a simplification because I have separated these things in a way that I can get something that is local and something that is not local. Okay, but it is how it is. And then when you look at the pressure, how the pressure acts on the rate of strain tensor is something that depends on how the rest of the fluid is moving around. And actually, the flow is incompressible, so you know that any point in the fluid will affect any other point in the fluid. And that's unavoidable. Of course, if the points are very far away, the interaction will, because of the pressure incompressibility, will not be very intense, but it will be there. Okay? And what you find when you look at the self-amplification is that whenever you have any topology of these characteristics, whenever by any chance you can generate something that looks a little bit like this, the self-amplification, the strain will interact with itself in a deterministic way to move things from this place to this place. Okay, to try to generate a topology like this from this topology, and this happens, as I said before, it's a deterministic process. And the only thing that can actually take things that are in this part of the QR code, so this topology, and move it to the other side to generate an inverse cascade is the pressure. Okay, that's the only mechanism, the only invested mechanism. Of course, I have removed the viscosity from here because I assume that we are in the inertial range of scales. Okay, the only mechanism that can generate, that can take this topology in the left and move it to the right is the pressure. And the problem with the pressure is that it depends on the rest of the flow, on every other point in the flow, whereas the self-amplification is something that is strictly local. And here comes the entropic argument. For the flow to generate this type of topologies from here, it has to be organized globally to counteract the action of the self-amplification at every point and drive all the topologies that are here to the other side. And now you can imagine why that is highly unlikely. Okay, turbulence is chaotic, and whenever you put a perturbation, let's say I have an inverse cascade, I put a perturbation, an inverse cascade that starts with all the topologies in this part of the tail. I put a perturbation there, and that perturbation will be expanded by the action of the pressure, not locally, and it will just that means that the pressure will not be able to counteract the self-amplification anymore, and everything will go from here to there. Boom. Okay, and well, the exact derivation of this entropic argument is in a paper in Journal of Fluid Mechanics. If you want to look at it more deeply, I don't have time to get into the details, but the take-home message here would be that the flow to generate an inverse cascade has to be highly organized, and it has to be organized on a global scale. Whereas to generate a direct cascade, it is enough it is enough to have a local mechanism that is actually deterministic. It's something that the strain interacts with itself to generate a type of topology that will lead the flow to go forward in time. And the summary so far is that the energy cascade is not a consequence. Well, the important part is that the energy cascade is not a consequence of dissipation. Okay, that dissipation is the cost. The energy cascade goes from the large to the small scales because of something that is even more powerful than dissipation, which is the entropy. It is just simply more likely for energy to go from the large scale to the small scales. And inverse cascade, as I said before, they can happen. Okay, they are there. It's a possibility, but they're highly unlikely. In the same way, there is a possibility that all the air of this room just compacts there into one corner spontaneously. There is nothing in the dynamics preventing that. Only that we know it will not happen because it's highly unlikely. And you can go to physical space and try to find out what is the reason for this to happen. I chose to look at the velocity gradient tensor, and in particular to the rate of strain tensor, which I showed is a good indicator of statistical irreversibility. And when you look at it, you find that the reason why the rate of strain tensor cannot generate a topology that will lead to an inverse cascade is the fact that the pressure needs to organize itself. So the flow needs to organize itself in a way that the pressure is acting at every point to prevent the self-amplification of the rate of strain tensor to generate a direct cascade. And this has implication for modeling and control. Well, the first one is control, of course. Entropy is a very powerful force. Okay, you cannot revert it. There is no way you can actually go out there and try to make things go backwards in time. Okay, so the moment there is any energy going into a cascade, that means that this energy has been lost to entropy. There is no way to make it come back. Okay, it means that it's going to be dissipated already. There is nothing you can do about it. This means that if you want to control turbulence, you have to do it in the large scales. You have to do it before the cascade. Okay, there is no way you can go to the cascade and try to change things so that all of a sudden you generate an inverse cascade and prevent dissipation happening. Dissipation is the same as friction, it's the same idea here. Okay, and it also has implications for modeling, which I will try to describe briefly because I ran out of time. It was a hot topic, I guess. Entropy and the implications for modeling, which I think are very interesting, is look, if the entropy is driving the cascade, and it is very unlikely that things just spontaneously go from the small to the large scales, this might be okay for modeling, because what I want to model is usually the large scales, because this is what tells you can get a lot of information from the large scales. You can get friction coefficients, you can get actually you can get the dissipation, you can get the energies. You're most of the time interested in the integral scales of the flow, and they can describe quite well the behavior of a fluid. And so now if the energy if the entropy is driving the cascade, and the entropy is a very strong force, I will not allow anything to go all the way back. This means that I can actually have some success at trying to model the energy cascade. The idea is, simulating turbulence is very expensive. You know it already. You need a very fine graining in the numerics. And what you do is you cut at a given point, you set up a cutoff scale, and you, instead of resolving the dissipation numerically, you just generate a model of the energy transfer. Okay, and you make sure that because of conservation of energy, this energy transfer is going to be the same as the dissipation, and well, this is going to sort of affect the large scales the way you expect, and you might get a result that is decent. And the fact that information or energy cannot go backwards from the part of the flow that we're not interested in to the part of the flow that we like or that we're interested in is good news. Okay, it means that modeling the cascade is something that might actually work. Okay. And how do you model the energy cascade? Well, you take the Navier-Stokes and you apply something that is called a filter. Probably many of you will be familiar with this idea. It's just simply a coarse graining of a space. Okay, you take some averages so that you remove all the information about the small scales. You filter Navier-Stokes, you do some manipulations, and you come up with something that is the advection of the filter velocity field, the pressure. Then you have a term that is related to the interactions between the scales below the filter and above the filter, and the forcing. Okay, and this term is usually called in turbulence research is called the subgrid scale stress tensor. Okay, and this is what we need to model because we don't know. This has all the information on how the small scales are affecting the large scale, or as one may see it, it has the information of how the kinetic energy is flowing from the large scale to the small scale. And well, you can calculate that equation, the equation for the resolved kinetic energy. You have also a conservation equation, a advection equation, plus some spatial fluxes. And then you can operate here on the energy and you get two terms. One that is something that is related to the advection of the subgrid scale stress tensor, minus a term that is called the subgrid scale energy fluxes, which is simply the subgrid scale stress tensor times the rate of strain tensor. And this term, if you average it over the computational domain, it will give you 0. It's a flux, okay? Unless you're putting something through the boundaries, it has to average to 0. And the thing that remains is this term here, which is associated with the energy cascade. These terms tell you actually the direction of the fluxes, where the energy is going up or it is going down. This is an energy, and you have here a minus sign. So when ds is positive, that means that the large scales are losing energy. That is, the energy is going from the large to the small scales. And this is actually what you see when you go to a direct numerical simulation or to an experiment. You can do this same filtering operation, okay? You can calculate the average energy production, and you see that it's equal to the average energy fluxes. And this is greater than 0. It's equal to the dissipation, you know, by conservation arguments. And this formalism actually works quite well to understand the energy fluxes in physical space. But okay, now you go to the flow, you're not only interested in the averages, but also what happens locally. You take this TS, okay, which is telling you at every point in space, it tells you whether the energy is flowing from the resolved scale to the unresolved scale, okay? And you compute a PDF of this in a direct numerical simulation or even in an experiment, and you see that in many places of the flow, you have a positive TS, which means energy is actually flowing the way you expect. It's going from the large to the small scales, okay? That's what we would expect from the energy cascade. But then what happens is that you also find that there is a very large fraction of the flow where things are going the other way around, where this TS term is actually negative, which means that there is a process, or there seems to be a process that is pumping energy from the unresolved scale or the scales below the filter to the scales above the filter. And you actually visualize them, okay? I mean, they look quite conspicuous. I mean, they seem to be there. You take the red spots here, direct energy transfer, this direct cascade, and you look at the blue structures, they are what is called backscatter. It's energy that is coming from the unresolved scale to the resolved scale. And this is something that I mean, it's quite surprising, and I think it even goes against my argument of entropy somehow, right? Because I have said, no, look, entropy is a very strong force. It is definitely driving everything from the large to the small scales. There's no way things can come from the small scales to the large scales. But now I do this, and there seems to be another flux. Seems to be a flux going from the large scale to the small scales, and another flux coming back. Okay, so there seems to be a double cascade. Okay, let's say, and backscatter is something that has been studied for a long time in the large scale simulation community. People that do models to resolve turbulence. And the problem is that it is very difficult to model, okay? Because it implies in many cases that you have to put there a negative viscosity, and that leads to instabilities, and the thing doesn't actually work. So people have been just doing models without any backscatter, and those work fine. Apparently, there is no problem. These models only take energy from the large to the smaller scales, but they still work fine. And the question is, does really backscatter represent an inverse energy cascade? Do we really need to model it? Is something that is there, or is maybe an artifact? Something that is not actually an inverse energy cascade, which, as I said before, is highly unlikely because of entropy, but something else. And this is what I want to show you in the last, I think I'm running out of time, but I want to show you in the last part of the presentation, which I think it might be interesting for people that do modeling. Navier-Stokes equations are a conservation equation. They basically tell you that momentum, the change of momentum in time is related to the divergence of some fluxes. Okay, and the problem with the fluxes is that they are not uniquely defined. Physically, we can only actually measure the change of momentum, but we cannot measure uniquely the fluxes, because I mean, the idea is simple. You take the fluxes that I have in the equation, I can add to that fluxes, I can add any flux with zero divergence, and those fluxes, the new ones I have generated here, will actually produce the same effect on the flow as the original fluxes. I cannot distinguish any of between the two of them. They are actually physically equally relevant. I cannot distinguish. This is a problem that has been known for a long time in electromagnetism, but I think has not been applied to fluid mechanics. And you can actually do the same thing for the subgrid scale stress tensor, which is again is a flux. It's a flux of energy, only that is represented in physical space. To the subgrid scale stress tensor, you can add any stress tensor with zero divergence, and you actually get the same result in Navier-Stokes. You cannot distinguish one from the other. So now the thing is, okay, since I know that I can change the subgrid scale stress tensor, what happens when I change it? What happens to the energy equation? What happens to the cascade process? How does it change when I change the definition of the subgrid scale stress tensor? Actually, nothing too important happened. Only that what was before something that is conservative, and what was considered part of the direct energy cascade now changes. Okay, the sum of these two terms, it's the same, but this term, okay, TS. So the standard flux can be completely different from the alternative fluxes that I define by just changing the definition of the subgrid scale stress tensor. And now, since I have the freedom, I have found out that I have the freedom to define these stresses the way I want, and to define the way energy is flowing to the smaller scales the way I want. I can actually go to the.
Where's the tau star? The tau star, where does it show up in the last equation?
So it's an alternative. Yeah. In this one, you mean?
Yeah, the tau star.
Yeah, the alternative is already TS times the tau star. This tau alternative is the subgrid scale stress tensor that are standard, and the ones that are alternative, which are the same as the standard ones plus something that has a zero divergence. So now I want to see if I can get rid of this backscatter by just simply changing the definition of the subgrid scale stress tensor. And for this, I set up a optimization algorithm, which is okay. I want this optimization algorithm to find the subgrid scale stress tensor that gives me the smallest possible variance of the energy fluxes. And you know that because the average, as I said before, has to be conserved. Okay, so the stress tensor has to change the average, because I know that the average is the same. If I reduce the variance of the fluxes, there will be a point in which there will be probably nothing left in the negative side. Okay, which is basically the same as taking this. As taking this PDF and try to make it, try just simply to narrow it. Okay.
Is there any physical reason to do so? It's like sounds like an engineering approach.
Yeah, I'll discuss. Yeah, I have said it many times, 10 times or more. Now I will talk about that afterwards. You simply flatten it, okay? Try to flatten the PDF, and well, you plug some initial condition of the Fourier scale stress tensor and try to see what you can get from it. And well, when you look at backscatter, the fraction of backscatter in the flow and the average backscatter, so the amount of points in which the flow shows an inverse energy cascade and the total combined magnitude of that inverse energy cascade, and you see that you can actually remove it, remove it almost completely by 4 orders of magnitude, okay? And here I show you one example of how this happens. You have the standard fluxes, is the blue line. This is exactly the same PDF as I showed before, the standard one, the one you do by doing the normal calculations. And this is after the optimization procedure. And you see that it's so flattened that the amount of backscatter that you have left is quite negligible. And you can get an idea of how dramatic or how drastic this reduction is when you look at a cut of a turbulent flow. These blue dots here represent backscatter. These red structures here represent the direct energy cascade. And when you go through the optimized fluxes, you get literally no backscatter. And now the point here is that these two representations of the energy fluxes are physically equivalent. They are the same. They cannot be distinguished. Okay, there is no way you can tell me, look, this energy transfer is not real. I like this one on the left. Okay, you cannot do that. I mean, they actually come from the same equation. There is no reason to distinguish them. And the summary of this, just to finish because I'm 5 minutes beyond the time. The summary of this, and maybe I can go back to the question of why I'm doing this. If there is a feature of the flow that depends on how you represent your equations, if that feature is not robust to the change of the definition of the stress tensor, okay, of the fluxes, then that feature might not be representative of the dynamics. And I am not saying that the fluxes without the backscatter are the real ones. I am only telling you that if I can find some fluxes or some definition of the Fourier scale stress tensor that doesn't have any backscatter, doesn't have any inverse cascade, maybe the inverse cascade does not exist. It's just a representational artifact. By the same reason that if I take electromagnetism, I cannot make the same thing. Okay, I cannot make this. I cannot find a representation of the Maxwell equations in which the things can go faster than the speed of light. Okay, it will be sort of the same thing. I know this approach is very engineering-like. Okay, it is. But if I give you this Fourier scale stress tensor that I found, and I tell you now you can compute the fluxes, and you find out that there is apparently to that definition there is nothing going the opposite way, that I think is a good way of saying, look, this might not be something that is robust of the dynamic, but it's something that depends on how you look at it. And something in science, if it depends on how you look at it, then probably might not be relevant. But okay, from the engineering point of view, or for people that are doing models, the take-home message for this approach is that you may not need to model any particular, you may not need to model a representation of the Fourier scale stress tensor that comes already from Navier-Stokes, but you are free to model any Fourier scale stress tensor that you want, provided that they actually fulfill the definition of a flux, which is the divergence of this new definition has to be exactly the same as the one that you get in Navier-Stokes. You have to model the divergence, not the stresses. Think of it, the divergence is a 3D flow, the divergence has 3 components, whereas the stresses is a 3x3 matrix. It's symmetric, okay? It has 6 components. So if you try to model the Fourier scale stress tensor you have there, you're trying to model 6 components per point in the domain, whereas when you try to model the divergence, it's only 3. So you might be trying to model things that are mathematical, but not physical. And this has quite an important application, is that look, if you don't want to model backscatter, you don't need to. There is no reason for you to do it. You can find a model that doesn't have any backscatter. This is good for people doing turbulence because backscatter is unstable and it's usually a problem. And it might be important for other features of the flow. There might be a feature that is difficult to model, but you might find a representation of the subgrid scale extensor that doesn't require you to model it. And to me, I know I don't have a direct proof of this, but to me this somehow shows that in the end, entropy is strong enough to even prevent these local inverse energy cascades. I know it's not a direct proof of it, but I think it shows that maybe backscatter is just an artifact. And that entropy in the end, or that the cascade is something that is strongly tilted from large to a small scale, and that is going in a very strong way only in one direction. And yeah, I had something else, but I probably gone over time. I will just give you a recent sum up of the publications. Where the first ones are related to what I talked about. I wanted to talk about the intermittency and coherence and structures at the end of the talk, but I was probably too optimistic with the time. So I'll just leave it here and I'll be happy to take any question.
Thank you very much.